I mean, I need to use in this example my thumb. Do you see the thumb, or is too small? Do you see it?
Yes.
Okay. The thumb describes the vector state. Okay? Just think to a vector state. But if you don't want to think about this, just use the following. You just use the vector state. Okay? Which is always in some, I mean, let's say orthogonal to the direction of the arm. Okay? Now, the rule is the following. I have to move the arm without twisting it. So I'm not allowed to do this. Okay? So the only thing I can do is just to do this, I do this, I do this, but I'm not allowed to rotate. Okay? Is this clear?
You repeat that.
So the rule of the game is the following. Now I will change the magnetic field. I will change the arm, but I'm not allowed in doing this transformation, doing this change, to do local rotation. So I cannot twist the arm. Okay? So I just move it like this. Do you see the thumb? I do like this, I do like this. Okay? I do like this, I do like this. So I'm not twisting it. I'm not doing any local rotation. Do you see this?
Yes.
Okay. So I'm transporting. So this is what I try to draw is parallel transport, because I'm moving the thumb in just keeping parallel. Okay? So I cannot do, I mean, I'm not allowed to do like this. So I just move it and rotate it. The only thing I can do is just do it like this. Okay? Are you with me?
Yes.
Very good. So now I want to do a cyclic change of the arm. So I start from here and I end up here. Okay? So suppose the following. I just do the following path. Like this, I go up, I go down. So I go on the other way and I go to the initial. So what is the final direction of the thumb as compared to the initial direction? I repeat it. Like this, ta-ta, ta-ta, like this. So can you tell me what is the angle of the thumb in the final point with respect to the initial point?
0.
0. Okay? Now I do the following. So unfortunately the camera, I mean, I'm not doing anything magic, so you have to trust me. I realize that I have to jump on the chair. Okay? Should I do it? Okay, otherwise you don't see it. So I do like, I do this other path. I go down, I do it like this, and come back here. So what is the angle now of the final minus between the final and the initial thumb?
90.
Sorry?
90.
90. So
But,
you see that.
But I think that you twist your arm.
No, believe me, I'm not cheating you. You try to do yourself, because I cannot stand. I cannot say all the. So you do like this. You go down. Okay, it's parallel. Then you do like this, and it's pointing in this direction. Okay, then you go down. Try to do it yourself, okay?
I kind of get your point. I mean, sorry. I think I kind of get your point because you're doing the parallel transport in 3 dimensions, so the angle has to change.
Exactly. This is the point. This is exactly the point. I'm moving in 3 dimensions. So if so I'm not doing anything spectacular, okay? So I'm trying to explain you that the motion of a quantum state, which is adiabatically transported along a cyclic change of parameters, after the cycle will be the same state up to a phase. The same will be in the same eigenstate up to a phase. And the phase, which is called Berry phase, depends only on the geometry of the path. Okay? Because the evolution, so let me say it this way, we are not going to work, I mean, to go in more details. Somebody, if you are interested, or some of you are interested, I will be happy to discuss, but we can do it in the next lecture because first I would like to finish a few things. Because Schrödinger equation, time-dependent Schrödinger equation, implements a kind of dynamics which is that of a parallel transport. So this, of course, it's an example. I'm not just pretending that this is quantum mechanics, but this is what I was trying to draw on the on the slides. Okay, so you can formalize parallel transport in the fact that the Schrödinger equation is such that the adiabatic state has the property that psi scalar product psi dot is equal to 0, where psi is the total state. So as a condition, as a consequence, the instantaneous eigenstate cannot go back to the initial state. Now, I have a question. So tell me what is clear, what is not clear.
So you're saying that because of this change, which is called Berry phase, and the instantaneous eigenstate also changes.
So the phase changes.
Phase.
the phase change. So it's in this picture is the angle, but so the phase changes. Now, the reason why I'm I'm saying this is that Berry phase appears as a concept which was discovered in the middle of the 80s. People did not realize, even if is something related to quantum to Schrödinger equation, people did not realize until Berry's paper. But Berry phase has been discovered in many different physical situations. So it leads to shift in spectra, in molecular spectra. It is related to some topological phenomena that appear in science. Did you ever heard about quantized Hall effect?
Yes.
Yes.
Very good.
No.
So quantized Hall effect is related to the existence of some, very good, everyone. So it assumes to some Berry phase like phenomenon. which is related to the wave function, to the electronic wave function in magnetic field. Okay, so this concept is important. Do you have other questions? Because I have to jump to a different topic. Okay.
So, do you work on this topic or?
Me?
Yeah.
I used to work I used to work some years ago.
I see.
Not now. But it's nothing advanced. I think it's important that you should learn about adiabatic evolution, this type of things, just related to quantum mechanics. It's nothing to do with my research interest. Okay.
Okay.
So, what I would like to discuss in these two lectures, before I go to this, I have a question. Now, if there is some aspect of the part on quantum mechanics which was not clear, you want to do it again, or you want, I don't know, just let me know, because we can have an extra of 1 or 2 or whatever extra lectures, okay, before the holidays. So you just tell me, okay? Not now. You just send me an email and say, well, we will like, or you just contact if you need to discuss about.
Professor?
Yes.
Actually, I have a question, I think, about the previous lectures.
Okay, but so let's do it later. Okay.
Okay.
Now, so what I would like to discuss today and tomorrow is some very basic, some important concepts related to many particle systems. Okay, so far you learn Schrödinger equation and essentially all the examples that we considered were related to single particles, an harmonic oscillator, hydrogen atom, the square well, all these type of things. Okay. Now, today, I would like to do a step forward. I'm pretty sure that all of you or most of you know what I'm going to say, but it's good to recap this. I would like to consider properties related to many particle systems. Okay? So, to consider a concrete example, you can imagine that you have just few electrons in some potential, and I don't know, some atomic potential, but it's not really important. Okay? So each electron will be described by some wave function. Then if we ignore any spin orbit or other effects, then it will have an orbital part. I just write it as a wave function and a spin part. Okay. So this is the orbital contribution. This is the spin contribution. Okay. So for instance, just imagine that you have plane waves. So if you have plane waves, the orbital part is just e to the I k dot r. And if it's, let's say, the spin is pointing along z up, then the spin part will be just an eigenstate of sigma z. But in general, you may have whatever we want. Okay? If you have hydrogen wave function, this will be, you know, the solution of the Schrödinger equation of the hydrogen atom, and this alpha will be will contain the corresponding quantum numbers. Now, just imagine, so let's start with the following question. So I want to write down the wave function of a system of non-interacting particles. Okay? So for some reasons, just ignore the possibility that, for instance, electrons are interacting because they have Coulomb energy. For the moment, let's ignore it. Okay? Now, if this is the case, then wave function can be written as, so for instance, I just write the, so let's call it this, psi, okay? Alpha of r. So this includes both. So I can say, okay, these are non-interacting. So if I have n particles, this will be psi F1 of R1, psi of alpha 2 R2, dot, dot, dot. Now psi of alpha n R n. Okay, so I just say, for example, the eigenstate corresponding, I'm having n particles or n electrons in given with given quantum numbers. It's just a product. Now, here we should do some more thinking that is related to a profound difference that may occur in quantum mechanics as compared to classical mechanics. Now, if you have two tennis table balls, I think you have played with tennis table down here at ICTP. So if you have two or few balls, are they identical? Y product? Just a moment, this is exactly what I'm going to say. So do you know about distinguishability, indistinguishability, and symmetrized and anti-symmetrized wave functions?
Yes, yes.
Does everybody know?
Can you tell us about more?
Okay, so the question of Jonah is exactly about this, okay? So I'm not going to say that this is the right wave function. I'm just going to say that this is my first attempt, okay? Now, let's go back to the question, is that, so if you have tennis table balls, and you have two of them, are they identical? Suppose they have the same color. I would say yes, they're identical. Okay, so if you take new balls, they are identical, right? However, if I ask you, can you distinguish them? What would you say?
I don't know, maybe it depends.
Well, tell me, why it should depend?
Because maybe the one is already worn out and the one is new. Who knows?
Okay, just imagine, let's consider the idealized situation. So okay. So suppose that my hands are the two balls, okay? And they are, at the beginning, they are in a given position. So you just label this left and this is right. Or this is 1 and this is 2, right? And then you give a kick to both of them and they will move. In their motion, can you distinguish them or not?
No. If they are identical.
Well,
If there is
but
nothing
if you have, sorry?
If there is nothing to distinguish between them.
Well, but for instance, if you have a camera, okay, very sophisticated camera, and you just record their motion, then you can trace back what was the path of particle 1 and what was the path of particle 2 of tennis ball 2 and tennis table. And if they hit, then you know that tennis table went, one went to the left, or I don't know, and the other went somewhere else. Do you agree?
Yeah.
If there is just 2, I guess.
Sorry?
If there is more than 2, you cannot follow.
No, but I'm saying, of course, you see, I'm not saying that you will be always able to distinguish. Of course, if you are on the moon, you will not even see the tennis balls. I'm just saying that if you have the right, I mean, if you have the right instruments, in principle, you can distinguish them.
Yes.
So suppose even with the eye, so if we have two guys, two persons, and I say, okay, I will follow tennis table 1, the other one is following 2, and then we just carefully follow the trace. In principle, if they go so fast, if they don't go under the table or somewhere, then I will be able to say what was number 2 and what is number 1. Okay?
Okay.
Good. So what I'm saying is that in classical mechanics, this is the statement. So tell me if you agree. Well, I will come to if they are numbered or not. Yes, in practice, when you look, they are numbered. Okay, you say 1 and 2. You don't need to write the number on top of it. Okay, so even if they are identical, they can be distinguished. Okay. So I'd like to hear a big yes or a big no or
Yes.
Yeah, it's true.
very good. So now I take 2 electrons, okay, and I put in a, let's say, in some orbital, okay. So in the 2p orbital, so I can put 2 electrons. You know the rules. So are the electrons identical? Yes.
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 Can you distinguish them?
No.
No. But now, why can't you distinguish them? So, of course, because they are, I mean, we are talking about a scale which cannot be seen. But the thing I would like to ask you is the following. Are you unable to distinguish them because simply you don't have a microscope which is so powerful, or there is something really fundamental which forbids you to distinguish them?
It's something that's fundamental.
And this is the right answer, It is fundamental because it's related to the fact that electrons, so for instance, if you put them in some eigenstate, I mean, you cannot attach, let's say, you cannot number them. So let me make another example with wave packets. So do you know what is a wave packet?
Yes.
Very good. So imagine that you prepare, so I put the time in this direction, okay? So you prepare 2 wave packets, okay? Just imagine that this is 1 and this is 2, okay? So you just prepare 2 particles with these properties. Now tell me, if you have only 1 particle, what happened to the wave packet when time goes on?
It decays.
No, well,
Sorry, Professor. Sorry, Professor.
yeah.
May you remind me about the wave packet?
Yeah, so I prepare a particle which is localized in space, say with some Gaussian, for example. Okay? So you just prepare psi, just imagine the following. You just prepare some state, I don't know, which is something like e to the minus in 1 dimension, x minus x1 squared with some 1 over n squared, and here there is a normalization factor. Okay?
Yes.
Okay, so you just prepare, just confine. That's not there. I mean, this n should be to normalize, and this L just give you there. So if you have an initial state like this, and so how the wave function changes in time? Yes, John, I read and it's correct. Tell me, but how the wave packet changes in time? What does it do? So it can do 2 things. So first of all, does it change or just remains with the same? Oh, sorry, this is t equals 0. Okay. So does it change or does it evolve? We are saying that the Hamiltonian is the free Hamiltonian, so it's p squared over 2n. Huh?
Yeah, it evolves, like it spreads out.
Very good. So it spreads. Okay. So when it goes with time, it becomes large. I'm exaggerating, otherwise I cannot use the the blackboard. Do you see this? Okay.
Yeah, yeah.
Okay. So the second one will do the same. Now tell me, can you distinguish the 2 electrons, the trajectory? I mean, not the trajectory, the evolution of the 2 electrons in time?
No, because they begin to overlap, I suppose.
Exactly. So since they become to overlap, at some point, it makes no sense to say this is the first electron, this is the second electron. Okay. So we have something which is very important here. That is, when we talk about identical particles, then in quantum mechanics, we have to take care the fact that these particles are indistinguishable. Okay? So at the end of this discussion, I will confuse a little bit. So I will come to a possible question that you are thinking now. So I would like to stress that something, so two objects being identical does not mean that they cannot be distinguished. Actually, in classical mechanics, this is something we know how to do. And they are distinguished because, and the reason is related that they follow trajectories, okay? So we can follow trajectories. If we take two pieces of chalks that smash, that scatter, and they move, we know that if this came from here, hits the other chalk and then moves somewhere else. So this chalk was the one coming from here. But if you have two electrons, for instance, you're not able to say, look, the chalk, if this chalk were quantum mechanically, you cannot say that the chalk that went up here was coming from down here or either was coming from down there. Okay? So we have to deal with so we have to understand on how to deal with indistinguishable particles. Right? Is this point clear?
Yes.
Yes.
Very good. So let's try. Oh, by the way, did you ever solve this problem of the wave packet just spreading?
Not
No.
sure.
No.
Okay. So do the following exercise. This is a nice exercise that you can do yourself. So just take e to the minus x minus x0 squared over L squared. So take the initial wave function like this. So the first thing you have to do is to find the normalization constant. Okay? And second, try to determine how psi changes in time. And so try to do let's say just a plot of psi p of the probability, which is just psi squared. Okay?
Yes.
Very good. So this is a simple exercise that it's good to do.
Professor,
Yes.
I think Jonah is asking question.
Sorry?
I think someone is asking question in the chat.
There was, sorry, Professor. Did you say we should plot? Yeah, the probability, yes. Okay. So try to understand how the probability, yeah, in time to be, for instance, in the initial. So you can plot whatever you want. I mean, it's not that. So of course, if I ask you the probability integrated over space, how does it change in time? If the probability is integrated over space, it does not change because the integral over probability is 1. Huh? Because it's normalization, change should not, therefore should not change. For instance, start in x0, which was the initial position, and see how it spreads. Okay. So something else you can do is the following. So, okay. So try to do the following. So just compute, this is nice. X, the average value of X as a function of time. Okay. And then also compute X squared minus X squared.
Is it related to the same exercise?
Yeah. So for this for this way packet, say instead of, let's say, you can first just took the probability in a given point and analyze a function of time. Something else you can do is just compute the average value and the variance as a function of time. Okay. So tell me, let's do, what is the average value as a function of time? Can you imagine? So think about it. This you can solve it without computing it. This you have to compute. Okay? Okay. So I would like to continue discussing this issue about indistinguishable particles from a slightly different point of view. That is, well, this is more formal, but it's very important. Okay. So the next example that I'm going to consider is the case of two particles, okay, that interact through some potential. Okay, so I have two particles. So the Hamiltonian is given by P1 squared over 2m. Do you see well, or since the blackboard is a bird, do you see what I'm writing?
I see very well.
Okay, very good. So plus VR1 plus P2 squared over 2m plus VR2 plus U of R1 of R2. Okay? So these are two particles that are in a given external potential V, and they interact through some interaction U. Okay? Now, the interaction I'm considering, I mean, so for instance, take Coulomb interaction, or is assumed, I mean, we know that this VR1 R2 is equal to V of R2 R1. So it's the same if you exchange the two particles. Okay? So I want to introduce now an operator P 1, 2 that exchange the two particles. Okay?
Sorry, Professor.
Yes.
Do you mean U R1 R2 equal to U R2 R1?
Sorry? Okay,
Do
can
you
you
mean, sorry, can you hear me?
yes, now yes.
I said, do you mean U R1 R2 equal to U, not V? I mean,
U R1 R2 is not is what? No,
is
sorry.
equal to U R2 R1. I mean U or V there. Yeah.
This is V R1 R2 is equal to V R2 R1.
Because in the Hamiltonian you wrote U of R1 R2.
Ah, sorry. Yes, you're right. Thank you. This is V. Ah, sorry. Let's call it U because V is something else. Okay. So yes, I meant U. Okay. Okay. Now, I want to consider this operator P12. This is an operator that exchange the labels 1 and 2, meaning that if I apply, this is will be the wave function. Okay. So let's say I have to put the vectors. Okay. So because but if I apply the operator P to psi R1 and R2, I will get psi of R2 R1. Okay, all these are vectors. Don't I mean, I will not write it. I'm just writing it here to be. Now, you agree with me that H of R1 R2 is equal to H of R2 R1, right? In this example I'm taking. Now, demonstrate, show, this is an exercise for you. Show the following, that P1 to H of R1 R2 is equal to H R1 R2 P1 2. What does it mean? It means that in this case, if I know that the Hamiltonian of 1 and 2 is equal to the Hamiltonian of 2, 1, then this operator P1, 2 commutes with the Hamiltonian. So this is something you have to prove. It's very simple. Okay, just play with it. Try to do yourself. Don't look in the notes. I mean, in the notes it's solved, but it's given as an exercise. But if you read it, it's trivial. It is more important that you try to do it yourself. Now, what does it mean that
Professor,
yes,
isn't that trivial? I mean,
yeah. I mean, the concept of triviality is something non-trivial. If it's trivial, then I mean, this is up to us to decide. But let's say the consequences are non-trivial. Okay.
I see.
So tell me. Let's discuss about the consequences. first of all, can you tell me the eigenvalues, the possible eigenvalues of the exchange operator P? Now, if you apply it twice, what does it mean? P squared. What is P squared?
P squared eigenvalue is 1.
So now the operator, I'm right. Now the eigenvalue is 1, but as an operator, P squared coincides with what?
The identity.
The identity.
Identity.
Right?
Yeah.
Because you exchange and then you exchange again, you go back to the initial situation. So the P squared should be the identity. And so the eigenvalues is 1. Now, from here, can you tell me what are the possible eigenvalues of P?
It's plus minus 1.
Now, the possible eigenvalues are plus minus 1. Moreover, if P commutes with the Hamiltonian, what can we say about the properties of the eigenstate, for instance?
They have same eigenstate.
Very good. So P, so the wave functions should be also eigenstates of P, right?
Yes, yes.
Very good. So let me make an example, okay? Suppose that you have two electrons, I don't know, two particles, and I put this in the state alpha 1 and this alpha 2 in R2, okay? And I just call this the wave function, phi R1, R2. Can you tell me, is this an eigenstate of P? Huh? Hello?
Sorry, what's alpha again?
Two quantum numbers. Okay? So I just have two orbitals, for example, with quantum numbers alpha 1 and alpha 2. Okay?
Then no, I think.
So this is not an eigenstate of P, right?
Yeah, because of the different quantum number.
Very good. So if I apply the P, I will just get psi of alpha 1 R2, psi of alpha 2 R1, which is different. So for instance, if you have a square well, and so you have a quantum number n, and you put one particle in the ground state and the other particle in the first excited state, this would not be a good solution because it does not satisfy the fact that it should be an eigenstate of P. Okay? In particular, I go back to what we said before. Now, since this operator, so I will have two possibilities, plus 1 as the eigenvalues and minus 1. So in some cases, wave function should be symmetric under exchange of particles. So first of all, we learned that this is not good. So this is not a good solution. The only possible solution are those for which the wave function is either symmetric or antisymmetric. Okay?
Yeah. So
yes.
It should be superposition, like Sorry.
Just a moment. Now you tell me what I should write. So this is not a good solution. So tell me what are the possible.
I think it's like 1 over square root of 2 in the bracket psi alpha 1 R1, psi alpha 2 R2, and you reverse the coordinate or the quantum number.
Plus minus?
Yeah, plus minus.
Right?
Yes.
Alpha 2 over 1 psi of alpha 1 R2. Okay? This is what you said, right? So you see that if you take this combination, now both the positive and negative sign will give you a correct symmetrization or anti-symmetrization. Okay? Now, this is something I think you studied or you're going to study or in statistical physics and other courses, you know, oh, I don't see the alphas where yeah, P1 when we have 3 identical particles. So, Jonah, I will answer you in a second. Okay, I finish what I was saying and then I answer to you. So, I'm sure you know this. Okay. So symmetrization or anti-symmetrization then is something which is linked to the spin of particles. Okay. So and so particles with half-integer spins, they are called fermions and obey anti-symmetrization, while particles that have integer spins, they are called bosons, and their wave function is symmetrized. Now, you're asking, so John asked, P12 change when we have 3 identical particles. So you can define any permutation of indices, okay? So let's not call it, so if you have 3 identical particles, basically the only thing you're asking is that how the wave function of a given configuration of given ordering of indices is related to a permuted one. Okay, and now we are going to see how. Clear? Okay, very good. So did you know, of course, about bosons and fermions? Huh?
Yeah, a bit, I think.
Okay, so you will learn more, I think, in the next courses. But the most important thing is that I stress it once more. This is not just a curiosity, but this will have an enormous impact on the properties of many particle systems when they behave quantum mechanically. So, according to the language and to the discussion we have been accustomed so far, the only thing I can say is that, you see, since interference is important, we are considering cases where you have superposition, and so the plus of the minus sign will play a role in observables. So if you measure properties of groups of bosons, they may behave completely differently from groups of fermions. Okay? So did you study boson statistics and Fermi statistics in the statistical physics course? Or this will be done later?
Just previous class, I think.
Okay. So did you study that if you go higher in temperature, then both statistics become like Boltzmann?
Yeah.
Okay. So in what we are saying, so do you know what does change when you change the temperature? So you can associate some kind of Broglie, the Broglie wavelength. So it's called thermal de Broglie wavelength, which essentially tells you the kind of the departure from quantum or classical states. So when you go to higher temperature, then do you know that Bose and Fermi statistics then become more or less equal to the Boltzmann statistics? Huh?
Yes.
Huh? Okay.
Yeah, it was just discussed in the previous class.
Okay. So this is related. So a picture in which you can get is related to the fact that you have an effective de Broglie wavelength, which should be compared to the interparticle distance. So given the density, you have some average distance between particles. And now you see that when you go up in temperature, this de Broglie wavelength becomes smaller and smaller. And so when it becomes much smaller than the interparticle distance is the example of wave packets, then indistinguishability loses to play a role, and so you have some classical behavior. On the opposite, when you go to low temperature, of course, this depends on various parameters, density and what's all these things. But when you go down in temperature, then basically this wavelength becomes comparable or much larger than interparticle distances, and then indistinguishability becomes important. Not only not only the fact that they're identical, which is always the case, but they become essentially indistinguishable. And so you have a strong departure from classicality. Now,
Professor,
yes.
are you saying that indistinguishability only play a role in low temperature physics, but not in high temperature or high energy physics?
No, I'm saying that I'm referring to the example you consider. Okay. So I'm referring to the equilibrium statistical to the statistical distribution. Then the discussion is much more complex. So in general, in equilibrium physics, the answer is yes, because this de Broglie wavelength is inversely proportional actually to the square root of the temperature. Okay. And so higher the temperature, the smaller effect of indistinguishability are. Okay. But the discussion is not like this. So I would not consider in such a simple term. In equilibrium is basically like this. Okay. Now, what is the temperature scale at which quantum effects appear to be important? Then this depends on the nature of the particles. I mean, the mass, the temperature, the density. Okay. Then there may be other different important. What I'm saying, what we are discussing now, is the case of non-interacting particles. Then, if you put interaction, things may change. Okay. Now, I would like to go to Jonas' question and make a step forward and I'm going to write how the wave function for a good wave function for n particles should be. Okay? N identical particles. So I simplify a little bit the notation just to keep it simple. So I will consider the state alpha 1, alpha 2, alpha n. Okay, I just write the ket. I do not write the wave function. I just write the ket. And these are the quantum numbers. They can contain anything, everything, also the speed. Okay. Now, what I'd like to do is just to do a permutation. Okay. So a permutation applied to the state alpha 1, alpha 2 will give me alpha p1, alpha p2, alpha pn. Okay. Not yet. It's not the state. What is a Slater Gudermia? I will come to that. Okay. So the Slater Gudermia you see only in the antisymmetric case. So if you have n particles, how many possible permutations do you have?
n factorial.
Very good. So if you take this wave function the same way we just wrote before, is not a symmetrized, that is not either symmetric or antisymmetric. So in order to write a symmetrized form, then so this is not good. So sorry, this is correct. Sorry, it's not. This is correct. So the correct form, let's say alpha 1, I can put it here as S or R. So saying symmetrized or anti-symmetrized form will be something like this. Should be equal to 1 over square root of n factorial sum over all the possible permutation of p applied to alpha 1, alpha n, and here I have psi to the power p, where psi is either plus or minus 1. Now, plus 1 is for bosons, minus 1 is for fermions, and essentially P, just count the number of exchanges that you have to do. Oh, sorry, there is a mistake here. This is P1 and this is Pn. That connects alpha P1 Pn to alpha 1 and alpha n. So this is a proper symmetric or anti-symmetric version of the wave function. Now, in the case in which you have psi to the minus, psi equal -1, this is nothing else that can be written as a determinant. This determinant, it's called Slater determinant, as yes, Varelis. So, okay. So it's a Slater determinant only in the case of Fermi. Okay. So shall we write? So is this clear? Hello? Ivan, okay.
So epsilon here to distinguish between fermions and bosons. So to distinguish between the symmetry.
Sorry, let's move. This sign is called psi, not epsilon. Okay?
Also the psi, yeah.
Psi, yes. So psi +1 refers to bosons, and psi -1 refers to fermions.
So can you repeat the P,
P
yeah.
is an operator.
No, the small p.
Small
Psi
p.
p. Yeah.
Psi. No, this is psi. So this is like this. So I'll just write it differently. This is +(-1) to the power p, where p just counts the number of permutations that you need to bring to the initial, to some reference configuration of indices. Okay. So let's say if you have 1, 2, 3. Okay. So one permutation is 1, 3, 2. Okay. Then you have 3, 1, 2, and you continue. Okay. So if these were bosons, 1, 2, 3, suppose that this is the reference configuration. Okay. So 1, 2, 3. So all the bosons will have a plus sign. Now for fermions, 1, 2, 3, it's +1. Then 1, 3, 2 is what? You exchange 1, it's -1. And 3 to 1?
+1.
It's +1 because you did 2 exchanges. Okay. And so you can define in this way all the relative signs. Now, this is just by, I mean, it just starts from 1 to 3. It does not really matter, because if you start from another configuration, another ordering of labels, this will just bring a overall phase factor in front of the wave function, and the overall phase factors do not play any role. Okay.
So, Professor,
Yes.
you're meaning the +-1 are the one telling us the symmetry and the antisymmetry in the thing?
No. Let's try to do it. Okay. What I mean is the following. Okay, so look, let's do the following. Let's apply this rule to 2 particles. Okay, so if I have 2 particles, so n is equal to 2. How many terms we have here? We have only 2 terms, okay? Because n is just 2. So if we have two particles, I have 1 over square root of 2, and then I have 1, 2. So alpha 1 and alpha 2. Okay. Oh, I'm going to. Sorry. I'll just write it here. So I have 1 over square root of 2, and then I have alpha 1 and alpha 2. Then the only permutation that I can have with two particles is that I have alpha 2, alpha 1, and I have plus minus alpha 2, alpha 1. Okay? Now, let's try to do with three particles. Okay? So I start and you continue. So with three particles, that the normalization factor is square root of 3 factorials. Okay? Then I start with alpha 1, alpha 2, alpha 3. Then I have the permutation in which I have to consider all possible permutations. So the first one I consider is plus minus alpha 1, alpha 3, alpha 2. Okay? Then I consider another permutation in which I exchange 3 and 2. So there is another plus minus sign. So I get the plus sign, alpha 3, alpha 2, sorry, alpha 3, alpha 1, alpha 2. So how many do I have? I have 6. So I have to work out and try to write down the wave function. Okay.
Why is it just plus in the last?
So if you so tell me to go from this from 3, 1, 2 to 1, 2, 3, how many exchange you have to do?
2.
2. So if you do minus 1 to the power 2, what do you get?
Yes, 1. Plus
You get 1. Okay. So this is why you get 1.
But why the second term you have plus and minus? Because we just need one
Because you change
one step.
okay, so it's minus 1 to the power 1. So it's either plus 1 to the power 1. So the number of so the even number of exchange will contribute to always a plus 1. The odd number of exchange will give you plus 1 or minus 1, depending if you have bosons or fermions. Okay.
No, I mean with your logic. So the second term we just need one step to come back from the second term to the first one. So it should be
So this one will
the second term to the third term to the first term.
yeah. So you have
So you
always,
just need only one. So it should be minus. So why you have plus?
so you have minus if you have fermions, but if you have bosons, it's always plus.
Oh yes.
Okay. So this is either plus or minus. Plus is for bosons. For bosons should be always symmetrized. So for bosons, you have
Yes,
all
yes.
possible
I see.
combination with pluses.
I see.
Okay. With fermions, you have pluses and minus depending on the number of exchanges.
Yes, I see.
Okay, very good. Now let's write. I mean, essentially here we have this later determinant, but I want to write it. Let's say for historical reasons, later determinant refers to when we express the wave function in real space. So and I write it. So just imagine that you have the wave function of n particles, which depends on n coordinates and all these quantum numbers. So this, I just rewrite it in just square root of n, sum over p, then it's -1 to the power p, and then you have psi of alpha, of p alpha 1, of alpha p1 of r1, psi of alpha p2 of r2, da, da, da. Okay, so I'm just rewriting what I wrote before, alpha pn, but with wave functions. Okay, instead of writing alpha p1, now I just write it the wave function. Okay, this is nothing else than the way to compute the determinant. So you can always write as 1 over square root of n factorial the determinant of psi alpha 1 r1, psi alpha 2 r2, psi of r1, psi alpha n r1. Then you continue psi of alpha 2 r1, psi of alpha 2 r2, and so on and so forth. And here you have psi of I'm making, so let's write, so this is alpha 1 r2, and this is r1. Okay, and this is psi alpha 1 r n. This is, sorry, I'm just making a mess, so I better rewrite. So this is psi alpha 2 r1. This is psi alpha 1 r2, alpha 2 r2, psi alpha n r2, and this is psi alpha 1 rn, and so on. This is psi alpha n rn.
Yes, sir.
Okay, so you can write what I wrote here as just as Slater determinant. So a determinant. This is called Slater determinant. Now, yes.
Oh, sorry to take you back a bit, but what is alpha p1, alpha p2, and alpha?
So alpha p1 is so can I give you one example to make symbol? Okay, so I have alpha 1, alpha 2, alpha 3. Okay, this will correspond to the configuration 1, 2, 3. Then I do the following permutation, which is 2, 3, 1. Okay, so this will correspond to alpha 2, alpha 3, and alpha 1. Okay, so in this case, P1 is equal to 2, P2 is equal to 3, and P3 is equal to 1. Okay, so is the index 1, 2, 3, n, which will correspond to the permutation P. Okay,
Yes.
Now, what happened if two rows have, or two columns have the same, are the same to the determinant?
0.
Very good. Now you see that this is the direct observation of something which is known as Pauli Principle, which applies to fermions. So you cannot have two states, two particles in this with the same quantum numbers. This is something you know, okay? And the Pauli Principle is reflected in the structure of the later determinant. Okay, and this is related to the anti-symmetrization of the wave function. Okay. Now, try to do the following. I start writing the wave function for 3 fermions. Okay, just work it out for all the systems. Okay, and let's do the following. So instead of having alpha 1, alpha 2, and alpha 3, you just define alpha 1 equal, let's call it L, alpha 2, it's L, and P, not P, kappa, and you do it for bosons, okay? Because for fermions it's nothing, while you just take this for bosons, okay? Then you try to write down the same thing for L, M, K, for 3 fermions in different states. So you just assume that you have 3 wave functions: psi L, psi M, and psi K. Okay, just write down 3. So the wave function in the 2 cases I wrote. Now there are 2 things that I need to tell you now. Okay, if you have so what we wrote here is something for which is valid for non-interacting. So this symmetrized, anti-symmetrized form.
Sorry, Professor.
Yes.
Can you repeat on the exercise we have to do?
Yes, you have 3 particles in 3 orbitals. The orbital, I call it LMK. Okay, so you have to write down the wave function for 3 bosons being in L, L, and K, and 3 fermions which are L, M, and K. Okay.
Is that alpha 1, alpha 1, alpha 3?
This is alpha 1, alpha 2, alpha 3. Or you can call it alpha 1, alpha 2, alpha 3. In one case, you have it alpha 3, or okay.
So for fermions, you have written L, M, and K, or L, M, and L?
So in the case of bosons, you have 2 equal orbital and 1 different, and you just call it LK, sorry. In the other case, you have 3 different orbitals, you call L, M, and K. Or you can call me whatever you want. Okay.
And what do you want us to find?
You have to write down the wave function, the symmetrized and or anti-symmetrized wave functions. Okay.
Yes.
Very good. So we continue tomorrow, okay? At 11. Bye-bye. Have a nice lunch.
Bye, Professor.
Professor,
Yes.
there is a question from Jonah.
Sorry. Quick. For later time is the board of the so no, because I mean you do Born Oppenheimer and then you keep track of anti-symmetrization of the electron wave function. Actually, it is very interesting because what I told you about Berry phases, for instance, is something which appears at the level of Born Oppenheimer. Not the way you are going to study or you already studied, but because there you have the motion of the nuclei, which is in a sense periodic, it will induce a kind of extra gauge field on the electrons. Now, I think Jonah's question leads me to one observation which is very important. What I wrote here is only valid for independent electrons. Okay, so these electrons do not interact. If we have an interacting electron, of course, this type of what I wrote here does not apply because cannot be expressed just a simple combination of single particles. However, since anti-symmetrization and symmetrization is something still there, what I wrote here in terms of symmetrized and unsymmetrized wave function is still it is very important because it allows you to write the good basis over which you are going to write down the many body wave function. This is something we are going to see a bit better tomorrow. Okay. Okay. Bye bye. Any more questions?
I think no. Goodbye, Professor.